Okay, so we can move to the next one, which is given by Mike Poland at USGS, and is the Kīlauea gravity experience, results and opportunities. So thanks, Mike, for giving this talk. And
thanks, Daniel. You can hear me and see everything okay?
Yes.
Great. Well, good afternoon, everyone. Thanks really much for inviting me here. It's been really fun to sort of observe the Newton G project over the years. It's obviously really exciting stuff with the development and the instrumentation and the modeling and the new insights and cool results from Etna. I'll share a little bit about our experience at Kīlauea today in Hawaii, and especially over the last decade doing gravity measurements, microgravity measurements to look at change over time. It's a bit of an odd talk for me to give, especially to this audience, because most of you know more about this than I do. I mean, Elska started doing gravity at Kīlauea 20 years ago. Daniele has been doing modeling and analysis of the continuous data sets since the day we installed those things. Marco Bagnardi has really set the stage for the campaign work, and Matthias is now taking it to another level, looking at all of the data that we collected during the summit eruption at Kīlauea over that 10-year period, and Mehdi and Eleonora doing really amazing modeling work. So I feel a little bit odd talking about some of this to people that know a lot more about this than I do, but I'll do my best to make it entertaining and informative. I know it's sort of the end of a long day. So thanks for hanging out with me, and I hope you find this interesting. All right, so first, just a bit of an update on, or a background on Kilauea's recent history. So the magma system at Kīlauea, magma rises from the mantle and it accumulates beneath the summit in a series of storage reservoirs. And from 1983 to 2018, it flowed out the East Rift Zone underground and erupted at the Pu'uo'o vent. And over that 35-year period, it put out nearly 4.5 cubic kilometers of lava. Starting in 2008, we also had a summit eruption where a pit crater formed at the summit, and lava lake rose into that pit crater and rose and fell, often in conjunction with what was happening out on the East Rift Zone. Now in 2018, a dike propagated from Pu'uo'o down into the lower East Rift Zone, where it erupted somewhere in the neighborhood of 1 to 1.5 cubic kilometers of lava over the course of a few months, destroyed 700 homes. It's one of the largest eruptions at Kīlauea in the last several hundred years. When that happened, Pu'uo'o collapsed. It fell apart as the magma supply went away from Pu'uo'o, and the summit lava lake receded, and eventually the summit collapsed as well in places by over 500 meters. And when that eruption ended, Kīlauea went quiet for about 2 years. In fact, a water lake formed at the summit as groundwater returned to the summit area, but that all ended in December of 2020, when first there was an intrusion and then an eruption within the pit that formed in 2018, seen here. That lasted until May of 2021. Then we had another intrusion in August, and a new summit eruption began in September of this year and is still ongoing. So we seem to have gone into a period that we sort of saw in the 60s and 70s, where there's repeated cyclic summit intrusions and eruptions. Now, microgravity work at Kīlauea started really in the 70s. There had been some gravity surveys to look at density structure of the subsurface prior to then, but the first real measurements of microgravity with respect to trying to get change happened in the 70s, 1975. And in fact, it was done just weeks before the magnitude 7.7 South Flank earthquake. And so immediately after that earthquake, some of the geophysicists went out and got more gravity data, and they were able to look at the change over the course of that event. And I'm highlighting a paper here by Dan Zarishan from 1980, where he says that simultaneous leveling and microgravity observations suggest that 40 to 90 million cubic meters of void space was created within the summit as a result of the earthquake. Now, this was one of the first results that I'm aware of that combined deformation measurements and gravity measurements to get at this idea of what was really happening beneath the ground, unequivocally getting rid of this question of vertical deformation. And this finding of void space is something that you're going to see again and again throughout this presentation, is something that we believe is pretty common at Kīlauea. And what we've been doing over the last decade especially is a combination of work, campaign measurements using, especially since 2009, Syntrex meters, mostly CG5s. We do have some CG6s, although we've discovered some problems with their calibration factors, so we haven't really used those yet. And then continuous measurements, mostly using Lacoste-Romberg meters, like this one right here, spring-based gravimeters. In terms of campaign microgravity at Kīlauea, I'll spend a little bit of time talking about our campaign results. As I said, that began in '75, and full surveys of this network with all these yellow dots over here were done in '75, '81, '98, '03, and 2008 using Lacoste-Romberg meters. And then there were very frequent measurements of a subset of caldera area stations, mostly between the Hawaiian Volcano Observatory, which is up in this area, and the caldera floor down in that area. That's something that Elska was doing when she was working at HVO. After 2009, we started doing full surveys a bit more frequently. This was in conjunction with the onset of the summit eruption, which was occurring right here in Halemaumau crater. And we were using these Syntrex gravimeters to track changes associated with that summit eruptive activity. Now, looking at that time period from 1975 up to 2008, before the summit eruption began, here you can see in the south part of the caldera, this is deformation. Over much of that time period, the ground was going down and gravity followed suit. We saw, this is residual gravity, saw decreases in gravity that suggested a decrease in mass. So that all made sense. The ground was deflating, mass was leaving the system, saw decreases in gravity. And then right in this period right here, towards the end of the time series, we had an increase in elevation due to an increase in magma supply to the volcano. And that had a corresponding gravity increase as well. But if we went into the center of the caldera, we had a slightly different story. So this is stations that are right towards the center of the caldera near Halemaumau crater. Again, we still had overall subsidence with a bit of uplift at the end, but gravity over this time period increased during this sequence. And the conclusion here was that we were seeing magma accumulation in a shallow reservoir, a reservoir that we know to exist from geodesy, from deformation measurements. And it was accumulating, the magma was accumulating in void space. So we were essentially replacing air with magma. That's why we weren't seeing much in the way of deformation of this shallow magma body, but we were seeing a mass increase there from the gravity. After the summit eruption began, we started doing these more frequent surveys. And this is work by Marco Bagnardi, who did some of these surveys and modeled all of the results. You can see his time series of vertical deformation, which we derived from INSAR, and deformation, gravity change in these gravity stations that are right near Halemaumau, which is essentially over the shallow source of magma accumulation beneath the caldera. And there's this gradual increase that eventually tailed off. And the model that he developed to explain these changes was that initially we had this very volatile rich reservoir, about a kilometer or so, 1 to 2 kilometers beneath the surface. Now, when this summit eruption occurred, that provided a pathway directly to the surface, and volatiles began to be lost from this reservoir. And that allowed a densification of the magma. We went from a volatile-rich reservoir to one that was in more of a steady state. And that can explain why we see this gravity increase during a time when the elevation changes were not necessarily quite as large. So in this case, not so much magma filling void space, but magma losing some of its volatile load and becoming slightly denser. We also have done quite a lot of continuous work at Kīlauea, and that's where I'm going to spend most of the rest of the presentation, telling you some pretty neat results here. For the most of the time, we had 2 gravimeters that were running. One was right on the rim of the summit eruptive vent in the caldera, and there was another on the rim of the Pu'uo'o eruptive vent out here on the east rift zone. At other time periods, we had other gravimeters running at the summit, but they were never consistently operating. Now, one of the most spectacular first results we had with the continuous gravimeter at the summit was published by Daniele several years ago. And so what you're seeing here in this video is a thermal camera looking at the summit lava lake. An intrusion and eruption occurs on the east rift zone, and that basically taps the magma from the summit. We see draining into that east rift zone. And here's the gravity signal during this exact same time period. So a great gravity decrease as the lava lake drains away, exactly what we would expect. Well, we know the geometry of this system right here. We know the geometry of the summit vent. So because we have the gravity, because we have the geometry of the vent, which Daniele modeled right here, and because we know the level of the lava over time, which is we could pick from this video, we're able to calculate the density of the lava in that lava lake. Now, the fit we get is quite good when we assume a density of 950 kilograms per cubic meter. That's less than water. And it suggests that this lava lake was a very gas-rich lava lake, which in fact is the sort of thing that we were observing because there was obviously very abundant bubble bursting and so forth in that lava lake. So this was an outstanding result that we had because this gravimeter was sitting right on the edge of this lava lake. Now that gravimeter continued to run through 2015, 2016 time period. And so something that Daniele was able to do was model the long-term change in gravity. I had to assume a certain drift rate to get rid of that. And we were only looking at short time periods, correlating that with lava level. And you can see in this time period here, the great correspondence between lava level and gravity change. So we're really seeing mostly the effects of lava level change in that summit erupt event. So by using that model that he developed to look at the draining of the lake and combining that with the gravity, we're able to look at the density of that lava lake over time. So there are the initial measurements from 2011, right about 1. And for the most part, it's sort of hovering around that area between 1, 1.5 for the density. Occasionally we get these spikes. And some of these were associated with increases in seismic activity at the summit and may in fact reflect small intrusions. So this may even provide us a method of seeing intrusive activity that we might not be able to detect in other ways. Some of these had geodetic signals or deformation signals, some didn't. There was usually some seismicity associated with them. So certainly pointing to gravity as another tool for perhaps looking at some transients that we might not know that much about otherwise. We also looked at gas piston events. Now, these are events where the lava lake suddenly rises and falls. And you'll see an example of it in this movie here, where the lava lake sort of looks like it's pulsing. The thought here is that these are driven by gas accumulation beneath the crust. And I'm sorry, hang on a second. If I sit too long, my lights turn off. So what's driving these gas piston events? Is it really gas accumulating beneath the surface of the lava lake? Well, this is something we can test. Sorry, there we go. So here is a map of the lava level change over time. This is the gravity over that same time period. Now, during these sorts of gas pistons, the lava level rises by up to 30 meters and then drops suddenly. We see this repeated behavior. And if we filter this gravity signal right here, we can see that each one of these gas pistons is accompanied by a slight gravity increase and then a drop, and an increase and a drop, and an increase and a drop. And because we have that great model of the geometry of the lava lake, the summit erupt event, and we know the changes in level, we can start to model this and try to understand the density. So if it were 0.4 in terms of the density, water being 1, this is the kind of signal we'd see. 0.3, 2, 0.1. And based on this, it looks like that portion of the lava lake that's changing elevation actually has a density between 0.1 and 0.2. So an incredibly gas-rich system, very much a foam. And that supports this idea that these gas pistons are being driven by gas accumulation beneath the surface crust. Then we come to the 2018 summit collapse. And we have the same sort of view here. This is the thermal camera. And over the course of several days, the summit gradually drained into the east drift zone. And you can see that gravity decrease occurring as the lava lake goes down. And this was one of the largest gravity changes that we're aware of in terms of measured continuously. It was slightly over 1 milligal over the course of several days of gravity decreases. Not only did the lava lake drain away, but tremendous amounts of magma in the subsurface drained to feed that lower east drift zone eruption. And during this time period, the summit caldera went from looking like something like this, looking like this. And that's where that 500 meters of drop occurred. Unfortunately, we did not recover this gravimeter, which was sitting right there prior to this collapse. And the gravimeter was lost to the collapse. So the gravimeter gave its life to recover this record. But it was not in vain. We were able to do the same sorts of things as we had done in the past in terms of the density of the lava lake this time, but we had even more accurate measurements. This is a map of the summit eruptive vent that was obtained through structure for motion work that Matt Patrick, the geologist at the Hawaiian Volcano Observatory, did. Now, he acquired these before the caldera collapsed, but after the lava lake drained away. So this is really a view of the interior of the lava lake. And once again, Daniele was able to model this exact geometry. And here's a sort of a plan view of the geometry. That's where the summit gravimeter was located. And using the changes in gravity over this time period and the lava level, we were able to model that change in gravity. We get a density of somewhere around 1.7 for that upper 200 meters. This suggests that there was a density increase over time of the lava lake. And that is consistent with perhaps what we've seen in some campaign gravity data. I mentioned Marco's results earlier, as well as the gradual sort of densification of the lava lake based on losing gases over time. So this seems consistent with some of our observations from other methods. Now, the exact same thing happened out at Pu'uo'o. The area collapsed. Matt Patrick flew out and was able to get structure for motion imagery of the vent before it fully collapsed. That geometry is shown here. There's the plan view. That's where the Pu'uo'o gravimeter was. Fortunately, this one did survive the collapse. Here's the model of how that sort of modeling works, where you have all of these elements and you can sort of change the level of the crater floor over time. So there's the gravity signal from Pu'uo'o. And in fact, this one we think might be the largest gravity change ever recorded over a short period of time by a continuous measurement. We had over 1.5 milligauss of change with this particular event. Now, we were able to model this by assuming the change in level over time. You get that right here. And based on that level over time and the gravity change and the geometry, we come up with a density of about 1.9 for the lava that was in the Pu'uo'o vent. And this actually makes sense. It's slightly denser than what we're seeing at the summit, which is consistent with differences in the elevation of the lava lake at the two places, and the fact that we had lots of evidence for pre-eruptive degassing at the summit. So gases were coming out at the summit, and then the magma was moving through the east rift zone and showing up at Pu'uo'o slightly degassed, so slightly denser. So this is all beginning to tell a pretty consistent story. But there's something else really, really interesting about this particular signal, and that's this small little bump that's before the big collapse starts at Pu'uo'o. All of the lava lake draining was during this time period right here, when Pu'uo'o shows this really massive gravity decrease. But what about this signal right in there? We zoom in on this, it's not a small signal. Gravity first went down by 200 microgauss and then went up by 400 microgauss. This is tilt measured at Pu'uo'o across the same time period. And this is about an hour prior to the collapse of Pu'uo'o, prior to the time period when the dike started moving down towards the lower east rift zone. So in many ways, this is the very first event of this incredible 2018 sequence. A very noticeable gravity decrease and gravity increase occurring at a time when there was some tilt going on, there was some deformation going on, but this signal here is just unequivocal, huge. One possibility for what this might have indicated is a small eruptive fissure that formed on the flank of Pu'uo'o. So here's Pu'uo'o after it's collapsing, but you can see this sort of steaming area on the west flank of Pu'uo'o, and that is a very small eruptive fissure. So this bears some similarities to measurements that have been made on Etna by continuous gravimeters, where you see changes in gravity as a dike passes beneath an area, first creating a dry crack and then filling that crack. Now, Daniele attempted to model this signal using that same kind of scenario and wasn't able to recreate this. So there's something different going on here, some combination perhaps of draining of lava lakes and emplacement of eruptive fissures. It's not clear with only the one instrument what was going on, but it is clear that this gravimeter detected something really strongly anomalous going on before the big collapse. And so I think this is a really nice argument for the power of gravity as a monitoring tool. If we had been looking at this gravimeter in real time, which we weren't at that time, we might have known something really anomalous was up, since we'd never seen such a signal out there before. All right, now on to the opportunities we have at Kīlauea. And it's a very exciting time at Kīlauea, and it really started after that summit collapse. So in November of 2018, Marco Bagnardi went back out to Kīlauea and did measurements at a series of benchmarks that did survive the collapse. And there were still a good network. In fact, many of these benchmarks are on this downdropped block here. They sort of rode the block down during the collapse, which is very piecemeal, occurred over several months. Now, Elska and I went back in March of 2019 and we duplicated Marco's survey. And we found that there was a gravity increase centered on that point in the middle of the caldera, as usual, reflective of mass accumulation in this magma reservoir that's about 1 to 2 kilometers deep. This is the same reservoir that drained to feed the 2018 activity. Over this time period, when we looked at our data from our 2 gravimeters, we got about 40 microgals of gravity increase decreasing away from that point. What's really fascinating about this gravity increase, it occurred during this time period here. This is vertical elevation change at a GPS station that's co-located with that gravity site. Over the time of the gravity increase, there was effectively no change in vertical elevation, no deformation, but there was a gravity increase. So we caught the gravity increase prior to the time when the ground started moving up. So that's a suggestion that gravity might have been telling us that the system was recharging prior to there being widespread uplift, which certainly happened right after our gravity surveys, and widespread seismicity. The model we developed to explain this, here's what the summit system looked like prior to collapse. There's the caldera, there's the summit eruptive vent, and then the whole thing fell apart as magma drained out to feed the lower east drift zone eruption in 2018. Now, after that activity ended, there started to be recharge. But that recharge was just filling all the void space of this chaotic jumble of mess from when the caldera did collapse. So the first thing we saw was gravity increase as that void space started to fill. Eventually, the void space filled sufficiently that we also had inflation, uplift. And so the gravity was the first indicator that recharge was coming, and then we saw the inflation once the void space had been sufficiently filled. We also have now some continuous results. Unfortunately, the continuous gravimeter wasn't operating during the first post-2018 summit eruption, the December 2020 to May 2021 eruption, but we got it back up and running. And certainly at the end of September, I think it was September 29th, we had a new summit eruption. You can see that occurring right here. This is deformation. So there's the summit of the summit caldera area. So that's deflation right there is when the summit eruption started. And this is the gravity record at the summit. There's a bit of tidal residual in here and a bit of drift residual, but before the eruption starts, we've got a bit of a gravity signal here, and then a signal in this time period that may be associated with rapid filling of lava in this crater, and then perhaps back to something more steady state. So there's clearly some signals. We haven't really started diving into this yet, but there's clearly some signals associated with the return to eruptive activity at the summit. Sort of interesting now because you can see that it's mostly filled, that big collapse pit at the summit, and it's going to start spilling onto the edge of that downdropped block where some of our gravity stations had survived. And in fact, our continuous gravimeter is right in this area here. So if this current eruption continues and perhaps at the point where the next eruption might happen, we will probably have to evacuate this gravity station because it will be inundated by lava. So this is the way we've been doing gravity at Kīlauea for the last 10 years or so. We've got continuous gravimeters generally sitting on the surface. We try to protect them as best we can. They're Lacoste and Romberg, spring-based gravimeters, D and G meters. And we've been using Syntrex CG5s and hopefully soon CG6s. I mentioned we've had some calibration issues with them and sent them back to the manufacturer. Hopefully we'll get those back soon and can start using them. We have a couple of new, refurbished Lacoste and Romberg meters. So we hope to be supplementing our continuous network with additional spring-based meters. But the real exciting thing is happening next month when we are going to take delivery of our first, as if there'll be more, we're taking delivery of an AQG. And so we will have the ability to do absolute continuous gravimetry at the summit of Kīlauea. We're going to set it up near the site of the old Hawaiian Volcano Observatory to collect continuous measurements and also to do campaign measurements as needed around the caldera. And then, of course, following Newton G, there's great hope that one day we'll be able to be deploying MEMS gravimeters. You could imagine if we could deploy these sort of low-cost gravimeters all around the summit, the kinds of signals we might see based on the sorts of things we've seen just over the last 10 years, especially as we're in this really exciting period of summit activity where we have repeated intrusions and eruptions. It's an incredibly dynamic place right now, absolutely perfect for gravity, given all the activity that's happening at the surface with lava lakes and the fact that the magma storage area is only 1 to 2 kilometers deep. So we can see signals from this. So campaign data have been really great in tracking these long-term changes, often associated with magma filling or draining from void space. This goes back to 1975. And the continuous data have provided some really neat insights that we wouldn't otherwise have, like the density of the lava lake as it controls various processes, transient events like intrusions, and I think really interestingly, a huge signal associated with the onset of the big 2018 event. And I think that really emphasizes the important role that real-time gravity can have as a volcano monitoring tool. Now, Kīlauea has returned to this cycle of summit intrusions and eruptions. It's just like it was doing back in the 60s, 70s, early 80s. So it's just a perfect time to be doing gravity at Kīlauea. There's all sorts of neat signals, all sorts of processes that we might be able to record. And we've got this exciting development of an AQG that will be delivered next month. And hopefully within the months to follow, a couple, 2 to 3 Lacoste and Romberg continuous gravimeters that we'll deploy in various places around the summit. We also hope to do new surveys, especially once we get the CG6s up and running. So nothing but opportunities at Kīlauea. It's an exciting time there. And hopefully we'll be able to build off of the tremendous success that the Newton G group has had. So thank you for blazing that trail. And thanks for allowing me to take part in part of the project. If there's time for any questions, I'd be happy to answer any if there are any.
Thank you very much, Mike. Questions for Mike first, and then maybe also for Marvin.
I would be curious for anyone out there that is using CG6s repeatedly. I mean, I saw Marvin, you were using those. We've had some trouble with them. The secondary calibration factors have not been stable. We've done surveys on calibration lines and found hundreds of microgals of change over just 2-month periods, which really gives us pause about using them. We sent it back to Syntrex. They are trying to diagnose the problem, but haven't figured them out. They sent us 2 new CG6s to replace the ones that had the calibration problem, but we haven't been able to fully test those yet. So I know I talked to Daniele about this, and he mentioned that there hadn't been any problems with the CG6s at Etna, which is reassuring. But the Hawaii CG6s seem to have the same issues. So we're sort of in a bit of a gravity head scratching mode with respect to those instruments right now.
Yeah, I think with respect to the CG6, we have like the older versions, so the orange ones. And we had some issues, but with the internal temperature sensor, we just got ours back from Syntrex 3 months ago, and they seem to work fine. I haven't gone to a calibration line with them so far, but all the newer ones, the blue ones, they were quite stable. So I don't know, you're laughing, but I don't know which ones you're talking about.
we have the blue ones, but you're making me want to paint it orange. Yeah, we have the blue ones, and they work great in individual surveys. They're outstanding in individual surveys, but survey to survey, we've seen just tremendous changes, hundreds of microgals over even just like a month and a half, 2 months, and clearly not real. So we don't really know what to make of that.
Yeah.
Mike, you have a question from Jeff Kennedy in the chat.
Yeah. Okay. Talk about the running the Lacoste and Romberg meters continuously in that environment. Yeah, it's not the best environment for instrumentation. At Pu'uo'o, which was a tremendous amount of gas coming out there. We put the gravimeter. We basically made a kind of broke through the lava to make kind of a flat area. Put concrete down. Stuck a pelican put a pelican case into the concrete and then poured concrete in the bottom of the pelican case and then put the gravimeter in there. And we were able to close it and seal it really well. So it was protected from gas emissions. But you could see basically the doghouse approach that we used at the summit of Kīlauea, because we couldn't make big modifications there. And the gravimeters have to be refurbished every once in a while. They start getting corroded from the acid gases. And that's especially true of the metal pieces on the top, like the reading dial and the clamping dial and so forth. They've worked for years, but yeah, every so often we had to send it back to have it refurbished, cleaned up a bit. So it's not the best environment. If you can put it in a sealed container like a pelican case, then I think it's a lot better. We did have problems with them going off level from time to time, but that was one of the really nice things about the Lacoste-Romberg meters, as opposed to some other continuous meters. You can record the levels, and so you know when they've gone off level, and that's an important thing to be able to say. All right, we know that we can't trust the data from here, or we should go out and re-level it.
More questions?
I think Daniele has his hand raised, but I don't know if we have time. Up to you.
So yes, just a few comments on gravity, about gravity on Kīlauea. I mean, there are 2 points that are important to stress. One is that you have seen that at Kīlauea we can have really huge gravity changes, which were in the past were mostly related to the lava lake. So it's something that has never been recorded at Etna, for example. This huge change by 100 of microgauss in a matter of few hours or few days. So it's something which is really very interesting from the point of view of continuous gravimetry, naturally. And another comment is that Kīlauea, there is a very good point about making continuous gravity measurements at Kīlauea, is that the ambient temperature is very stable through 1 year, compared to Etna, where we can have yearly temperature changes by 20 microgauss and more than that, maybe. So this is another very good point. So since the temperature is very stable, the effect on spring gravimeters from ambient temperature of a long period, it's relatively small. So this is another good point about it. I was thinking during this talk by Mike, maybe we should discuss the possibility to install some MEMS gravimeters there. If we cannot make it to Etna because the snow is arriving fast. So I think that until the spring, we won't be able to install any MEMS gravimeter, at least in the summit zone of Etna. So we could consider this possibility.
It's always a good time to work at Kīlauea, and I mean that in every sense of that word.
Especially now, if there is all these changes occurring, it could be a very nice time. So we could discuss this possibility for sure.
Well, the last time we went through these phases of summit intrusions and eruptions, it lasted for decades. And so hopefully we'll have sort of very interesting, neat science eruptions and intrusions for, years to come that aren't threatening to the population, but allow us to learn a whole lot. So hopefully it'll be like a wonderful volcano lab for the next few decades.
Yeah. So this is a possibility that we should for sure consider. Any other comments?
Well, thanks everyone, and congratulations on the Newton G project. It's really fun been exciting to watch everything develop.
Thanks a lot, Mike.
Thanks a lot.